We're now going to move on to talking about stability. Stability is one of the primary considerations that you have to think about in choosing a scheme. And people have developed methods for sort of trying to get after the stability itself and quantify that in terms of the CFL number. And this is where the CFL is going to play a huge role in determining schemes and also determining the relationship between accuracy in space and how I can step in time. So let's get to it. So stability is critical, and so the scheme you want to pick is determined by the stability itself. So what you want to do is get a stable scheme which allows you to take as large a time steps as possible, right? So some schemes will give you stability, but will also require you to have exceptionally small time stepping delta t. And so if you have to take a very small time step, it means your solution, if you're going to evolve this up to some fixed time capital T, it's going to take you a lot longer to get there if your time step is 10 times shorter than some other scheme. I mean, it's going to take 10 times longer to solve the equation. So accuracy and stability are intertwined, and stability is your primary consideration initially in picking a scheme. So let's talk about how we might compute stability. How they've done this traditionally, and this is an important aspect of numerical schemes, is by doing what's called a von Neumann analysis. And even though the von Neumann analysis doesn't necessarily carry over to all the complicated nonlinear PDEs we might solve, von Neumann analysis tells us something very important about the types of schemes that we might want to be considering, including, for instance, the difference between if you have waves or heat or diffusion. They're very different schemes that work in these two classes of physics-based systems. So the idea behind the von Neumann analysis is take your solution, U of nm. So remember, m, the superscript, tells you at what time point you're at. The n is the spatial point you're at. And what we're going to do is we're going to break it up into essentially what looks like exponentials here, or Fourier modes in space, with a coefficient g of m. So as we iterate forward, this solution, g, a constant, is being raised to the mth power. So we're going to plug this in as the solution to the PDE, and what we really care about is that g. In particular, as we go forward, as m goes to infinity, what you care about is what happens. G is raised to the nth power. So as you march forward, or many, many steps, if g, the absolute value g to the nth power, goes to infinity, you'd say that's an unstable scheme, because in fact your solution is going to go to infinity. However, if g raised to the nth power is less than or equal to 1, then that means that this thing here will be a stable scheme. In other words, it's not blowing up on you. So it's a very simple criteria, and we can compute this explicitly for linear constant coefficient PDEs. And so this gives you a broad range of PDEs to consider, and what you really see from this is that in many PDEs, the kind of schemes you might use, whether it's a heat equation, diffusion type structure versus waves, you'd use very different schemes to resolve them or get a good approximation for them. So let's go through this and show this. So let's go through the Euler's one-way wave equation that we considered in the last lecture. And what we're going to do with this one-way wave equation, we're going to take the first discretization we did, which was forward Euler and center difference in space. And this was our scheme. This was this first scheme we developed in the last section. There's our CFL number right there, lambda. And what we're going to do with this is we're going to go ahead and put in that von Neumann analysis solution. So if you do this, you plug in that solution. Here's what you get into the scheme. We're going to now start simplifying, collecting terms. I have all these g of m's everywhere. I pull them out. And now I have this all collected here. I can multiply by e to the minus I c of n h through. I have this now simplified to here. I can now pull these two terms together into, in fact, what I do is rewrite this as zeta here, to shorten this variable up, and then I end up here finally with this expression here. G is 1 plus 1 I lambda times sine of this. Now if you look at the absolute value of this, right, so you take the absolute value, which is take the solution itself times its complex conjugate, square root, becomes this here, which this is always equal to or greater than 1. So we're basically in an unstable scheme. Remember, if G is bigger than 1, which is this is going to be for any finite lambda, so any finite delta t, essentially what we are in a situation on is this scheme is always unstable. There's nothing you can do to this scheme to make this stable. You march this forward, the solution will blow up. Later, we're going to actually program this up, and we're going to show you that it does, in fact, exactly that. You start marching along, your solution blows up on you. And it's right there in the scheme. Remember, you are setting iterations up as a proxy for these continuous variables. Not all iterations are well behaved. This here tells you this iteration scheme is going to be terrible for you to use. It is a forward Euler with center difference. In fact, forward Euler with center difference for any kind of wave equation is typically going to be always unstable. So you would never use this scheme for something like a wave equation or where you have hyperbolic systems with waves propagating around. Let's come back to it, and instead of doing the forward Euler, let's do the backward Euler. So this is just slightly different. So the only difference now is I'm evaluating this here in the future, not the present. So I did forward Euler before, backward Euler now. I do the same manipulations and narrow everything down, do some algebra, and this is now the expression I have here after I do my von Neumann analysis. So if you follow the algebra, which is not that intense, it's just a little bit of a manipulation to here, and then you look at the absolute value, here's what it is, and this thing is always less than or equal to 1. So now what do I have? Is I have a scheme that is unconditionally stable. It doesn't matter what do I do on my delta x, delta t, my CFL, it's always stable. So just this change here, and by the way, this also illustrates why people like implicit schemes. The reason people like implicit schemes is because this often happens, is that you get these amazing stability properties in implicit schemes, even though they're very difficult to solve because you have to solve the future in terms of the future, and it requires you to do some work like solve an ax equal b to do it, but this is what it typically buys you. So the forward Euler is always unstable, the backward Euler is always stable. Complete opposites, just by a simple change in the iteration algorithm here. What about leapfrog? So let's go through leapfrog. So same thing, just change the scheme, but now point front, point behind, and now center difference at the current time point. Again, you can plug all of this in, and now the expressions are a little bit more complex as you do the algebra. You get sort of now a quadratic equation for the G, and you can actually work out that this scheme, leapfrog 2.2, is stable provided the CFL number is less than or equal to 1. So when you're starting to think about that CFL, remember the CFL is delta t over delta x. This has huge implications. If you have to keep that CFL under 1, then if you want to get better resolution in space, in other words, you cut your delta x in half, you have to cut your delta t in half as well. Okay, that's for this one-way wave equation, because the CFL condition is delta t over delta x. So this has big implications in terms of if I want a certain spatial accuracy, I have to then think about what that means with my time accuracy as well. Okay, so what about Lax-Windruff? You can do the same kind of von Neumann analysis here. Here's what you find for that G. It's this complicated expression, and again, you can work out when is this thing, when you take a time step, you want this thing to be less than or equal to 1. Okay? So these are all the things you would want to consider in time stepping. And again, stability is critical. It's the first thing you have to think about in a scheme. If your scheme is unstable, you just can't use it at all. So the first thing you have to do is develop a stable scheme, make sure it is more common that you have a CFL restriction, that the scheme is stable provided the CFL number is below some value. Sometimes this is actually very hard to compute, sometimes it's easy. But once you have that, now you have yourself a stable stepper, and that is what really is going to determine the appropriateness of a scheme. So always keep that in mind. Your job isn't just march forward in time. I already showed you in the last lecture, we developed 6 different time-stepping schemes just for the wave equation, one-way wave equation, right? Which one should you use? Well, it's going to be determined by some of the stability criteria and the CFL numbers. And so what we want to do is think about the accuracy of the solution, the speed at which I can solve it, and the stability I have with that. So all these things are considerations in practical situations. So that kind of ends this section on stability. Once you find a stable scheme and you like it, then you can just concentrate on getting solutions to your system.